Okay, so now we have the reflection coefficient and the transmission coefficient. Now, it's important to understand what these terms mean. So the reflection coefficient is basically what we're imagining is that we have a beam of particles, all of them with the same energy. Okay, that means the same velocity, traveling. In this case, we've said the problem going from left to right. So they're incident upon this potential barrier, and the reflection coefficient is just the probability that any one particle will get reflected from the barrier, okay, rather than transmitted. The transmission coefficient is obviously sort of the inverse of that. What's the probability that a particular particle in the beam will get transmitted? Another way of saying that is, what's the ratio of the intensities? I mean, what's the ratio of the intensities? How much? What fraction of the incident intensity um, is reflected? That is, how many particles per unit time are reflected um, per per particles per unit time that are incident. Okay, so that's how you interpret that. So there's not a whole lot more to be said about these reflection transmission coefficients, other than to point out that K1 and K2 are functions of the energy and the potential barrier and the mass and etc. And so and so you can actually, if you're given a problem, you can solve for these in terms of E and U naught and whatever. And then and also the other very interesting thing to point out is that even though these are not bound states, we have a sine function, sine squared function in the numerator of the reflection coefficient. And so if we set that, obviously there are whenever you have a sine an oscillatory function, that means that it can be zero. So when K2L is some multiple of pi, then the numerator can be 0 here. That means the reflection coefficient is going to be 0, and the transmission coefficient is going to be 1. And so there are certain values of K2L that that lead to 100% transmission and no reflection. Okay, and that is basically what we expect actually classically. Classically, for any energy that's above for any energy E that's bigger than U naught, we expect the particle to slow down as it goes over the potential barrier, and then speed back up when it goes to the other side of the potential barrier, and basically it comes out and it never gets reflected. Okay, in quantum mechanics, we saw that we have some probability of reflection, but at these particular energies, we get 100% transmission, just as we would classically. Okay, so so again, when the energy is greater than U naught, then R equals 0 when sine squared K2L is equal to 0, and that implies that K2L has to be some multiple of pi. Okay, and K2 is just square root of 2m E minus U naught divided by H bar, and multiply that by L. And so if we solve then for the energy, we see that when the energy is equal to the potential height, potential barrier height U naught plus n squared pi squared H bar squared over 2ml squared, where n is an integer, then we get resonant, what we call resonant transmission, which means that we get 100% with 100% probability an incoming particle with that energy will be transmitted to the other side of the potential barrier, and none of the and 0% will be reflected. Okay. Now it's important to realize that although resonant transmission occurs only for some particular incident energies, namely these ones, okay, that doesn't mean that the energy is quantized. The energy in these problems can have any value. Okay, the incoming particles, the particles in the incoming beam can have any energy. Okay, but at these particular energies, you'll get no reflection and 100% transmission. At other energies, you'll get some reflection always. Okay. All right.